Welcome to Session 10. We've been living in algebra for 9 sessions. Today, we go visual. The SAT will hand you a graph and ask where two curves meet, or which curve is on top, or how many times they cross. And there's one idea that turns all of these into problems you already know how to solve. It's called the difference function, and it is genuinely the most powerful reframing in this course. We'll also talk about when a graph can lie to you, because a picture is evidence, not proof. Here's the idea. Instead of thinking about two graphs f and g, think about one new function. h of x equals f of x minus g of x. The difference. Now ask, where do f and g intersect? They intersect where f of x equals g of x. And if f equals g, then f minus g is 0. So h is 0. That's the whole move. Intersections of f and g are exactly the zeros of h. Read that again, because of what it buys you. You have spent years learning about the zeros of a quadratic. Factoring, the quadratic formula, the discriminant, eta, all of it is machinery for finding zeros. The difference function lets you point every bit of that machinery at an intersection question. Two curves become one curve, and crossing becomes 0. Now the difference function does something extra that's even more useful. It doesn't just tell you where the graphs meet. It tells you which one is on top. Think about it. If h of x is positive, then f minus g is positive, which means f is bigger than g. So f is above g at that x. If h of x is negative, then f is below g. And if h is 0, they're touching. So the sign of the difference function is a complete map of who's winning at every x. This is why questions like, for what values of x is f greater than g, are really just questions about where a quadratic is positive. Here's where it gets beautifully mechanical. Suppose the difference comes to you factored. H of x equals some leading factor times x minus r times x minus s. The zeros are obviously r and s. But now think about the sign in each region. Take a simple upward case first, like x minus 1 times x minus 5. To the left of 1, both factors are negative, and negative times negative is positive, so h is positive. Between 1 and 5, the first factor turned positive, but the second is still negative. Positive times negative is negative, so h is negative there. To the right of 5, both are positive, so h is positive again. See the pattern? For an upward opening parabola, it's positive outside the roots, and negative between them. Now if there's a negative leading factor out front, every sign flips. Negative outside, positive between. So, check whether the parabola opens up or down. And then remember, between the roots is the odd one out. Let's use it. Suppose f of x minus g of x equals negative 1 times the quantity x plus 2 times the quantity x minus 1. On what interval is f greater than g? F greater than g means the difference is positive. So we want where that expression is positive. The zeros are at negative 2 and 1. The leading factor is negative 1, so this parabola opens downward. A downward parabola is positive between its zeros, and negative outside them. So f is greater than g when x is between negative 2 and 1. Let's spot check with x equals 0, which is inside that interval. Negative 1 times 0 plus 2 times 0 minus 1. That's negative 1 times 2 times negative 1, which equals positive 2. Positive. So f is above g at x equals 0. Confirmed. That 5-second check with a convenient number is worth doing every time. Here's a third question. The SAT builds on the same setup. The axis of symmetry. If a quadratic difference function has zeros at r and s, where's its axis of symmetry? A parabola is perfectly symmetric about its vertex. The two roots are mirror images across that vertical line, so the axis sits exactly halfway between them. X equals r plus s over 2. Just the average. For zeros at negative 2 and 1, the axis is negative 2 plus 1 over 2, which is negative 1/2. And notice, this connects straight back to eta. The sum of the roots is negative b over a, so half the sum is negative b over 2a, which is the vertex formula you already know. Same fact, two derivations. When two different roots agree, that's your confirmation you understand it. One more graphical distinction, and it's a favorite of test writers. What if the difference function has a double root, like x minus 3 all squared? There's 1 0 at x equals 3, but watch the sign around it. To the left of 3, x minus 3 is negative, and squaring makes it positive. To the right, x minus 3 is positive, and squaring keeps it positive. So h is positive on both sides, and 0 only at the single point. The sign never changes. Graphically, that means the graphs touch, but do not cross. F comes down to meet G, kisses it, and goes back up. Compare that to a single root, where the sign flips and the curves genuinely cross over each other. So, double root means touch, and the discriminant is 0. That's our tangent case again, seen from a new angle. Now the warning. And please take this one seriously. A graph is evidence. It is not proof. Here are 3 ways a picture will lie to you. First, the window. If your view shows no intersection, that does not mean there isn't one. It might be sitting just outside the frame. Always consider zooming out before concluding never. Second, resolution. What looks like a single touch point might actually be 2 intersections that are extremely close together. Zoom in before you claim tangency. Third, and most common on the SAT, decimals hide exact values. The graph reports x equals 2.236. Is that the answer? Look closer. 2.236 is the square root of 5. If the answer choices contain radicals, your decimal can't match them, and you'll pick wrong or waste a minute. So use the graph to form a conjecture, and use algebra to prove it. Let's do one from your practice set. If f of x minus g of x equals -1 times the quantity x plus 2 times the quantity x minus 1, on what interval is f of x greater than g of x? Step 1, f greater than g means the difference is positive. Step 2, the zeros are -2 and 1. Step 3, the leading factor is negative, so the parabola opens downward, which means it's positive between its roots. So the answer is -2 is less than x is less than 1. That's B. And look at choice A, x less than -2 or x greater than 1. That's the answer you'd get if you forgot the negative leading factor and assumed the parabola opened upward. It is precisely backwards. The test writer put it there on purpose. Let's recap. Define h equals f minus g. The intersections of f and g are the zeros of h, which means every quadratic tool you own now applies. The sign of h tells you who's on top. Positive means f is above, negative means f is below. For a factor difference, an upward parabola is negative between the roots and positive outside. A downward one is the reverse. Always check the leading sign. The axis of symmetry is the average of the roots. A double root means the graphs touch without crossing. That's d equals 0 again. And a graph is evidence, not proof. Watch the window, watch the resolution, and watch for decimals hiding radicals. Great work on session 10. The difference function is a genuine upgrade in how you see these problems, and it'll serve you well beyond the SAT. In session 11, we get practical about the digital test itself, when to use Desmos, when to use algebra, and how to decide in about 2 seconds. See you there.